So we'll move to testing the serializability of the schedule. So we are going to use this algorithm which can test conflict serializability of the schedule. If a schedule is conflicting, we can say it's a serializable schedule. So see, basically what we are doing is we're converting all the transaction. This is a set of nodes, or we can say we are converting all the transaction into nodes, and we are going to have a set of edges. This is our graph where n is represents node and e represents edges. So and we have all the transaction as nodes, and these e are nothing but the edges between those nodes. See, let's begin with the algorithm. Basically, we already know that for each transaction Ti participating in the schedule, create a node labeled Ti in the precedence graph. So basically, we are gonna have if there were n transaction in a schedule, then we are gonna have n nodes, each corresponding to a particular transaction. And moving to the next step, what we're gonna do is if we are having an edge between Ti to Tj, and it's a directed edge, which means uh, Ti has a write item operation and Tj has a read operation before it. Basically, Tj executes a read item operation after Ti executes a write it. So basically, it has a write item as operation, and after that, Tj performs read operation. Similarly, we have the third step, we can say. Um, Here we are writing TJ after TI writes, reads, yeah, when TI first reads the item, and then we are gonna write it in transaction TJ, then there is gonna be an edge from TI to TJ. This is reading, this is writing, and in this case, this is writing, this is reading. So in both the cases, we're going to have an edge moving to right conflicts. So these three are the most, as we discussed earlier, there are three conflicts: read write read, and write write. So this is for read write, this is for write read, and this is for write write conflict. So after, I mean, it's basically both TJ writes with after TI writes. And at the end, if scheduled as serialized, if and only if the precedent graph has no cycles. If there are no cycles forming, and then we can say it's serializable. So this was the overall algorithm. I hope it's clear. It's not that complex to understand. Basically, they have explained what a cycle is. It's nothing but a sequence of edges, or as how displayed here, and I think it's clear to you guys, and I hope you majority of the viewers is gonna be computer science, and they, they may have encountered the DSA as one of their courses. We have cycle and graph theory. So in precedent graph, an edge from Ti to Tj means that the transaction Ti must come before Tj. And AC will schedule is equivalent to this. So if we don't find any cycle, I mean, in the precedence graph, we can create an equivalent serial schedule S prime that is equivalent to S. By ordering the transaction, the path displayed in S as follows. Whenever an edge exists, Ti must appear before Tj in an equivalent serial schedule S prime. So what they have said here is whenever an edge exists, see, this is very important point. In the precedence graph Ti to Tj, Ti must appear before Tj in the equivalent serial schedule. If you're obtaining a serial schedule as prime, then the relative order of the operations in both Ti and Tj should be uh, like analogous to this. To that, let's see. So these are the it's for yeah the which I showed earlier. It's for the diagram 20.5 which I showed in the previous video. So let's go to that part. Yep, with this one, as you can see, we have these two nodes T1 and T2, and if we are this is the right item, and then we are reading. So we are reading after it writes. So there is an edge between T1 to T2, and that's the directed edge. So there is an edge and coming to this point. So we are first writing in T2, and then we are reading it in T1. That's why there is an edge between. So that's we can see. And coming to C, reading and then reading. That's not a conflict, but if we write it, and if we are writing it, we are reading. If we are writing, what was it's a bit confusing. We have read-write conflicts. Or okay, so we are reading IMX. After that, we are writing it. So there is an edge between T2 to T1, and also we are writing IMX and writing IMX. So there is an edge between. So there is a cycle. Similarly, we can derive in schedule D. Let's move on. That's not difficult. Okay, so we are gonna name the edges by the by the data item which they are which conflict is occurring on, which leads to create the edge. So when we are checking for cycles, the labels are irrelevant. We don't need to consider it.